Good morning, ladies and gentlemen. I am Angelique Scallard, and I serve on the committee for the SAIMM Northern Cape Branch. It's my pleasure to welcome all of you to this webinar. What an excellent turnout. I would like to thank the following two companies, Metix and PESCO, for sponsoring this webinar titled The Characterization of Iron Ore and Manganese for Resource Optimization. The characterization of a mineral resource is the first step in determining the potential product grade and the product mass recovery as inputs to the process design. It is therefore critical that the characterization data achieved is representative of the resource and in line with the plant production technologies to be utilized. It's important to note that different techniques are applicable as the ore moves through the various characterization stages. Hence, this presentation will focus on the techniques relevant to the beneficiation of ores using dense medium separation technology. Our two presenters for today have extensive biographies, so the few words I'll say about them definitely doesn't do them justice. But here we go. Our first presenter is Mr. Pieter from Metix. He has over 30 years of experience, both local and international. His current role is a metallurgical/processing specialist on iron ore, diamonds, gold, HBI, and chrome projects. The main objective of these projects are to improve production performance and to generate the required characterization data for study completion. Mr. Pieterse also published a technical paper in 2008 titled Fine Iron Ore Beneficiation. Our second presenter is Mr. Jeremy Bosman, the Principal Process Consultant from Process Engineering Solutions Company, famously known as PESCO. He worked at Multitech for 16 years, managing the cyclone division for both local and international markets. He also lectured part-time at the University of Pretoria for 10 years. In 2003, he founded PESCO, a consulting company offering services to the mineral processing industry. Please note that PESCO also offers training on a range of topics, including dense medium separation, screening, and classification. Mr. Bosman has presented over 30 technical papers, locally and internationally. While that concludes the introductions, the following is very important. If you have any questions, please don't hesitate to post your questions in the Q&A section. The presenters will answer the questions after the presentation. So with that said, ladies and gents, you are in for a technical treat. I now hand over to our first presenter, Mr. Pieterse. Take it away.
Thanks, Angelique. I'm just waiting for Jeremy quickly to set up the presentation and then I'll start. Thanks, Jeremy. Okay, so as been explained in detail by Angelique, we will be focusing on ore characterization, specifically on iron ore and manganese. The content of today's presentation will focus on the following. So we will discuss the objective of characterization, what sampling and sample preparation requirements will be needed when you do characterization, look at the different mineralogies of the ore being tested, what assay techniques we're using to test the minerals, the beneficiation process that we'll be focused on, a testing overview of some test work that's been done, also look into density and gravity separation techniques and in a summary. I will focus on the first part of up until the assays, and Jeremy then will discuss the beneficiation process further on. So what's the objective of characterization of ore? The first objective is to identify the beneficiation properties of an ore. Can it be upgraded or not? And that will determine what grade can be achieved and what yield can be achieved. That input then will be put into various models to ensure that the plant designs can be complied to that information. The beneficiation process that we are focusing on today is gravity separation, looking at DMS or spirals, magnetic separation, wet drums or dry drums, magnetic separation. We know there's flotation on the fine side, but for today's discussion, it will not be done. So when you start characterization of an iron ore or a manganese ore, the first step would be to determine what is the required specification. What is your required grade that you want to achieve? So you'll see there we've got a red line. That's for 62% Fe. So that means that is the grade you want to achieve during your characterization process. On the right, you'll see an orange line. That's a beneficiation of a sample being tested. We call that the DSO, direct shipping ore. That material is already on spec and there's no beneficiation required for that sample. The second line is a blue line that was tested at different densities and showed that the sample did achieve grade at about 85% yield. It made 62% Fe. The bottom line is a sample that's been tested and did not make grade. It did not achieve the required specified product grade. Therefore, maybe additional characterization tests will be needed to determine if the top size, the liberation size, can be reduced to improve the yield and the qualities. Characterization is quite a detailed work in looking at the different properties of the ore to determine, can you put this material into your plant to make a product. And there's a lot of tests that we've done, seed float work and characterization work, design work, etc. But it's important that when you generate a sample, you must ensure that the sample that you generate is representative. So you spend a lot of money on a test work and your sample is not representative, you can definitely, you're going to waste a lot of money. So I think your various samples that you can get for a test work is from diamond drill cores, bulk samples through the plant when you put materials into the plant, and then stockpiles. So before you do any sampling, you identify the source, make sure what sampling techniques you're going to use on a specific ore body. I know there's percussion drill cores of RC drill cores. That samples is not representative of the ore. It's been break up, it's not sampled representatively. So to do testing on that would be a waste of time and money. So when you do sampling, you're sampling to ensure you've got a representative sample physically and chemically, and therefore you're using different sampling techniques. The sampling techniques will consist of automated sampler. When you send your run of mine through your process, you will take automated samples over a long period to ensure you represent the ore body. And then also you can sample from stockpiles, manual sampling, and then from drill cores. So when you look at the drill core, you will combine it in different lithological ore bench combinations. That's all be determined priorly before you do the test work. And it's also important when you look at your sampling, you don't work alone, you work with a geological team, a mining team, to ensure that you look at the resource and make sure that's part of the future plan for that operation. Sample preparation, that's the next step. So after sampling, you need to start prepare a sample. And also it's very easy to generate errors and ensure that and you have a sample that's not 100% representative of your test work. So samples will need to be crushed. I think it's important to understand what crushing you want to achieve. So before you will understand this, do I need to test for a 32mm top size, 35mm top size, or 1mm top size? And that's part of your crushing technique. Then you will split it to generate the required practical sample to be tested in the lab or the pilot unit. And you also screen the sample into various screen sizes. So as I explained before, when you do crushing, you need to know exactly what top size are you aiming at, and also let your crush sample represent what's happening in the plant. I know there's different types of crushes in the labs, and there's different type of crushes in the plants. So when you use your lab crusher, make sure you generate the same energy in crushing, generate the same type of liberation when you do crushing compared to in the production unit. So if you've got a jaw crush and a cone crush in the plant, use the same type of jaw crush and cone crush in the lab. Don't use disc crushers or high pressure grinding rolls or something else, because that will definitely influence the liberations of your material. Sample splitting. When you do test work in the lab, you don't want to work with a 1-ton sample, 2-ton sample. You want to work with something that's practical. So the moment you do any size reduction or sample reduction, there's also a good chance to generate the error in your sampling process. So it's important that you use the right techniques when you do sample splitting. Preferable for us is a rotary splitter that we'll use to split out a big sample and generate your sub-samples, have reference samples, and you can always go back and do additional tests if required. Otherwise, you're using a joint riffler or the cone quartering process. Screening is the final step in your sample preparation. It's to screen the sample in the correct size ranges. It's also important when you do your screening in the lab, also take into account the screen efficiencies. There's a certain screen efficiency you can achieve in the lab, and there's a different screen efficiency you're going to achieve in the plant. So it's always important to keep that in mind. Also, the next information you can generate from your test sample before you start doing the characterization is to confirm the fraction analysis, to determine in what size fraction most of your valuable mineral will lie. Okay, so after you've done all your sample preparation, you will start with your mineralogy. So the first step is to using an XRD. The XRD is used to determine the mineral phase of the sample. It's an X-ray diffraction that you illuminate your sample. There's a beam on the sample, and it will generate various peaks. You see on the right-hand side, there's a graph. That peak will tell you what type of mineral it is. And I think in the next slide, we'll show you some examples of the various minerals that you'll get in Fe minerals or a manganese mineral. Typical with iron ore, the XRD will tell you there's a hematite, a magnetite, or a limonite. You can see there's a clear difference between the Fe content of the different hematites, of the different iron ores. 69.9% for hematite, 72.3% for the magnetite, and a 60% Fe for the limonite. There's also a small difference in densities. If you look at the samples, you can see 5.3, 5.15. And I think that's what is hidden behind it. But I think it's about 4 something, the density for limonite. Mineralogy for manganese, quite interesting. You've got 3 different types of manganese. There's a pyrrolysite, jacobsite, and auspmanite. What's interesting is there's a significant difference in the manganese content. 63.2% in the manganese, 26.6% for the jacobsite, and auspmanite is 72%. That is minimal difference in densities, 4.73, 4.75, etc. This typical then that will make it very difficult to separate this type of minerals on a density basis. And I think that's why we know in some of the manganese process, we are using magnetic separation as very successfully. Next step is chemical analysis. We're using XRF. So the sample is exposed to a X-ray beam where different energy levels is generated. We all use the X-rays in our labs to determine the percentage Fe, manganese samples. So important for us to know is that the energy peak that's generated by the XRF will tell us what element it is. And then the intensity you pick up on that peak will tell you the quantity of that mineral in that sample. So if you have a 60% Fe on this slide, it will give you a high intensity that's been then referred to the percentage of that mineral. Chemical analysis that we use, as I just spoke now, we use XRF. But when you use XRF, there's also different methods of analyzing. Use a press palette or versus a fuse bead, or even some mines like to use a titration for Fe-based or manganese. It's very important when you do press palette and fuse bead that you understand there's also certain accuracy impacts on your XRF. With a press palette, your calibration is critical. You must make sure that you've got the right calibration for your type of mineral, your type of matrix. The moment you use fuse bead, that matrix is being destroyed, and you have a much more accurate analysis. From my experience, I worked at a lot of mines where they've got a very accurate press palette calibration. They start doing a new exploration project. They looked at a new area in a mine. That all's got a total different type of matrix. And when I analyze it on the same press bead, same calibration, sometimes generate errors of 5 to 10% absolute values on your element that you analyze. So it's very important that when you do your analysis on a new ore body, make sure that you first test it independently at the accredited lab or a third-party lab to make sure your analysis are correct. Also, for this example, I think it's important that we just also show you the difference in different elements of Fe for this example. So this is a graph showing Australian Pilbara Fe. sample, iron ore sample versus a Northern Cape iron ore. They got exactly the same Fe content, 64.1%. But if you look at the silica, alumina, the potassium, and the phos, and even the LOI, you will see the difference in these elements. A much lower silica versus a typical Northern Cape of 4%. Alumina, Northern Cape is normally between 1% and 2%. Porphyra, very low, 0.3%. The potassium in the Northern Cape is normally between 0.1% and 0.3%. Here we see the Porphyra of 0.008. That is quite, and I think that's important to take into account when you look at your minerals, what is the rest of your contaminants inside a sample. If you look then at manganese. Okay, sorry, before I jump to the manganese sample. So it's important when you do XRF and XRD that you do it in combination. The XRD looks at the mineralogy, tell you what type of mineral it is, what mineral phase it is. The next slide is your XRF that looks at the chemistry, percentage Fe, percentage silica, etc. And then you use a weighted average to identify that through the XRD. So when you complete your XRD analysis, you use your XRF analysis to make sure there's a balance. And that gives you much more confidence in your results. It will tell you exactly the correction factors you need to apply on your XRDs if necessary. So that's my part of the presentation. From this part forward, I will hand over to Jeremy. And yeah, thank you.
Okay, thank you very much, Pieter. So we now that we've covered the basic fundamental characterization of the ore types, you're going to go more into the beneficiation processes. And if we look at manganese, what we find is that there's different size ranges. So we have lump, and the size range is variable. It depends upon your ore body. It can be anything from a 75 mil top size down to a 30 mil top size, and the bottom size can vary between 8 and 20, but we have a lump fraction. We also have a fines fraction. And then we will have an ultrafines fraction, which would be typically the -1. If we look at the iron ore, you have lump iron ore, which can be 32 by 8 or 25 by 6. We have fines, which is 8 by 1 or 6 by 1. We have ultrafines, which is the -1 by 45 microns. And then we have the slimes, which is the -45 microns. Dense medium as a beneficiation process covers a size range from 100 down to 0.5 millimeters. So you can see it covers the iron ore lump, the iron ore fines, and a portion of the ultrafines, and that's where more of the development work is, and then manganese, both the lump and the fines. If we look at dry, high-intensity magnetic separation, that's specifically applicable to the manganese fines, where we use the magnetic properties of the manganese and the host material to upgrade the manganese content. Then spirals. Spirals are typically focused on the 1 by 45 micron fraction. And then reflux classifiers also overlap to a certain degree or to a large degree with spirals in the same size range. And then you've got WIMS, which is wet high intensity magnetic separation. And typically that's used on -1 millimeter ore. And it encompasses slimes as well. And then if you're looking at flotation, the flotation would be focused on the slimes. If we look at testing, we've got different scales of testing. So we start with bench scale, which literally is in a laboratory on a workbench, that sort of scale. You then can go bigger to pilot plant. We use bigger samples, and then from there you go to your full scale, which is your operation. And as you move from bench scale to pilot plant, your increasing sample mass and tonnage increases the confidence in the results that you produce. We'll focus on dense medium and the dense medium bench scale. What we find is that we've got 3 techniques that we can use on bench scale for dense medium. We can use individual particle pygnometry, we can use heavy liquid separation, and we can use QEM scan. You can see the individual particle pygnometry is valid above 10 millimeters. Heavy liquid separation can go down to 0.5 millimeter, 0.5, and then QEM scan is typically on -1 millimeter. If we look at individual particle pygnometry, and you'll see in this picture there's a crown shown as an example. And the legend goes that around 250 before BC, that they were in Syracuse. Syracuse is in Italy. It's on the southern part of Italy. There was a king, Hero, and he was presented a crown, a gold crown, as a gift, but he wasn't sure, and he didn't believe it was pure gold. And Archimedes also lived in Syracuse around the same time. So Hero approached Archimedes and said, determine for me whether this crown is gold or not. And what Archimedes did, he weighed it in air and he weighed it in water, and he worked out the density. So if we look at this, if you weigh the crown in air, this is example 14.7. When you submerge the crown in water, the weight is 13.4 kilograms. And then using this formula, we can calculate specific gravity, which is the weight in air divided by the difference between the weight in the air and the water. So it's 14.7 is the air, and then 14.7 minus 13.4 is the difference, and you get 11.3. And therefore, it wasn't gold, because gold has a density, pure gold has a density of around about 19. But that's the principle that we use for analyzing individual particles. So we do this on a particle by particle basis. Here's an example from manganese. So the size fraction was 32 by 10. The starting mass was 11.7 kilograms, and in that mass, there was a total of 1,216 particles. And after each particle had been weighed and its density calculated, it occupied the density range from 2.3 up to 4.3. So if we look here, we've got a graph of the results. On the x-axis, we have the different density bins. You can see they're 2.3 to 2.6, 2.6 to 2.8, all the way up to 4.3. Those lines represent the mass distribution. In other words, how much of the mass of the sample reported to each of those density bins. And then that line represents the manganese content. So you can see that the sample didn't have a great manganese content. We couldn't get anything more than 30. But what's interesting though, if we target in now on the 3.7 to 3.8 density bin, because we analyzed each particle individually, we can then get more detail on that. So we can break down that bin into 0.01 density fractions, and that's the density distribution within that bin. So the individual particle pignometry, because you're analyzing by particle, in terms of density, it gives you extremely high resolution. Here's the grade yield curve. You can see here, if you're targeting, say, a 30 or above, this sample wouldn't make it. Heavy liquid separation, that's basically you make up a fluid medium of different densities. You add the feed. In this example, your medium is 2.9, so you'll have a floats at 2.9, and the stuff that's heavier than 2.9 will sink. The floats, then you transfer to the next one, which is 2.85. So then you'll get the float, so the stuff that's heavier than 2.9 but lighter than 2.85 will float, and then you'll get the sinks. And so you continue the process. So here's an example of a float sink analysis of a Northern Cape iron ore. The density range covered was from 2.8 up to 4.2. And there was a mass distribution in each density bin and the Fe value. So you can see at the high densities, you've got high Fe. And as your density bin drops, or your density fraction that you're testing, the Fe drops. And then the silica has got the opposite response. So at high densities, you've got low silica, but at low densities, you've got high silica. This sample had a head grade of 59 Fe and 3.9 silica, but you can see the alumina was very high, 3.77. And that was one of the challenges with this specific sample. If we go and look at the grade yield curve, if we're targeting a 62.5 yield, our grade, you can see we've got a yield of around about 60%. And this is one way of representing heavy liquid separation results. There's another way which gives a bit more information, is what we do is we plot the cut densities or the densities on the x-axis. On the y-axis, we plot yield to sinks and the near density, we'll go into that. And then on the other y-axis, we've got Fe grade. So if we look at yield to sinks, there's my yield to sinks curve, which is a blue curve. Then your Fe grade goes from just below 60, we said it was a 59, up to there, the cumulative, that's your cumulative grade. And then here's near density curve, which is your plus or minus 0.05 of your cut densities. That's the amount of material plus or minus 0.05 of above and below your cut density. So if we wanted to make a 62.5 grade, we intersect the Fe grade line, we go down, we see we need a cut density of 4.1. We can go up and we can move across. We can say we're getting a 60% yield. And then when it intersects the near gravity line, we can see there's less than 20% near gravity. So this wouldn't be a difficult separation. The third technique, which applies to the -1 millimeter, is QuemScan. And QuemScan is really just an automated mineral analyzer. So here's a picture of a magnetite hematite iron ore. You can see, for example, the quartz is the pink stuff. So you can see that, for example, that particle is a fully liberated quartz particle. Hematite is a brown, so you can see there's some hematite, but you can see that there's inclusions in the hematite and there's all the other minerals. So how does it work? You go and you identify the minerals of interest. They've each got a chemical formula. So hematite Fe2O3, quartz, silica. You've got the density of hematite, for example, 5.26. And then each particle, when it analyzes, it says, okay, this particle is made up of several minerals. It works out the percentage of each mineral, and then it works out a weighted average density for that particle, and then reports it. And then at the same time, it can work out a weighted average chemistry for that particle. There's also other information that comes out of the QuemScan, is it can look at the specific particles, it can look at the circumference, different diameters. And so if you choose the equivalent circle diameter of the particles, you can generate a particle size distribution. So you can just see this particle of this sample was less than 1 millimeter, 1,000 microns. Sorry, that's microns, it should be microns or millimeters. And the 50% passing was about 800 micron. Here's the yield and the Fe. So you can see the yield drops down. So if, for example, if you've got a 4, if you could cut it 4, your yield would be about 85 and your grade would be about 66. So you can see this sample is actually very well liberated. The feed grade was just below 60, and you could generate up to almost a pure there's some pure minerals of hematite or particles of hematite in there. So when you do QuemScan work, and typically you'll use this when you're looking at your finer particles, you will also do XRD to assist with the mineral identification. But you've also got to be careful, because when you prepare the sample for MLA, you actually mount the sample and then you polish the surface. So you're actually looking at a 2-dimensional slice through the particle and not 3-dimensional. So depending on how the particles orientate themselves when you mount them, it can affect the results. If we now go into the pilot plant and we look at dense medium separation, for the lump, this is a setup that we have at PESCO. We have a WEMCO design drum. It can handle a top size of 40 millimeters, a bottom size of 6, and can handle densities from 2.9 up to 4.2, depending upon the medium grade that you choose. Fines, the fines, there's a 165, there's a cyclone up there, and a 250 millimeter cyclone. Can handle a top size of 12 mil, a bottom size of 0.5, and also the same range of densities, again, using different medium grades than you would with the drum. Here are some examples of a pilot plant drum test work on a Northern Cape conglomerate. So 3 densities were analyzed, were tested, and the floats and sinks were analyzed using XRD and XRF. So there's the floats and the sinks for the 3 densities. If we look at the hematite, we can see as the cut density increased, so the amount of hematite in the sinks increased, and the amount of quartz in the floats went down. So if you look at this at 4.2, we'd expect almost all hematite, and you can see there 93.5% hematite, not reporting any quartz in there, interesting enough, and a bit of kaolinite. If we look at the XRF corresponding, we can see that the sinks, the Fe value of the sinks, this went from 64.1 to 64.6 to 65.5, and the silica dropped from 3.9 to 3.5 to 3. And that's just one of the things that one must remember with XRD. It has a lower detection limit. So normally somewhere around 3%, it struggles to identify. So you can't use XRD if you've got trace elements to pick up the minerals. There's another pilot plant drum test on a Pilbara ore. The cut density was 2.8, and that was established using traces. The floats and sinks were analyzed using IPP, individual particle picnometry, and the efficiency was calculated. So the size range of this example is 32 by 16, so it's nice and coarse. The float's mass that was analyzed was 12.6, and the sink's mass was 21.6 kilograms. The number of particles in that 12 kilograms of the floats was 1,000. The number of particles in the sinks for the 21, it's double the mass almost, is 925. And that just shows you the impact of the density of the particles in the floats and sinks, which differ, and the number of particles that are in a certain mass. The floats then occupy density bins from 2 to 2.95, and the sinks from 2.75 up to 4.5. So in this case, you can see there the number of particles, total number of particles that were analyzed was around 2,000. And here's the distribution of the floats and the sinks. So you can see the floats, those are the light densities, the sinks are the higher densities, and then around the cut density, you have a bit of misplacement. If we take that further, we go and plot a partition curve. The blue dotted line shows the partition curve from the IPP data, and then the gray line is the whiten partition curve, which is fitted. So you can see the cut density was 2.82. We targeted at 2.8, so that came out very close. And the EP was 0.056, which is a nice sharp separation. We now move on to spirals, and the spirals just covers the size range from 1 to 45 microns. For bench scale spiral test work, you can use a shaking table. Here's a picture of a shaking table. So you get a concentrate which moves to the top, you get middlings, and then you get a tail. So that'll give you an idea of what the grade, you can take the samples off there, the grade and the yield is. But you must remember that the shaking table has got to be calibrated against an actual spiral result. If we move to pilot plant on a spiral, we actually use a spiral. So the nice thing about spirals is we can use a single start, and it's like a full-scale version. So we don't have any scale-up issues. Here's a picture of separation on a spiral with a middlings and a tail. So the concentrate, the heavy stuff moves towards the center of the spiral. You can see it's nice and dark. And then you take a cut, that'll be your concentrate. The middlings contain some iron ore and some unliberated particles that you take out the middle. And then the tailings is normally your light stuff, your silica, fine silica, and so on. And that moves to the outside. Reflux classifier, there's only we don't have a bench scale test for a reflux classifier, so you've got to do pilot plant only. And there's an example of a reflux classifier test rig that's down at the University of Newcastle in Australia. There's the lamellar plate, and then there's where the hindered settling takes place. Now, what's interesting at Gemco, which is Groote Eylandt mining company in Australia, they have a sedimentary manganese that they produce. They use drums and cyclones, and then what they used to call sands, which was the -1 millimeter they used to throw away. And then they did a project using reflux classifiers, and they've now installed 5 reflux classifiers which treat that sands at -1 millimeter fraction, and they produce a saleable product from it. If we look at dry and wet high intensity limiting separation, so that covers the manganese fines, as well as the iron ore ultrafines and slimes. Bench scale, you have a little unit like that. So you add the sample through there, you can adjust the field strength. So you can do it at 7,000, 8, 10, 11, 12, up to 15. And then your magnetic particles get held back and your non-magnetics go through. And so you can, by adjusting the Gauss setting, you can work out how much is recoverable. And then you analyze the products for the grade. On the pilot plant scale, here's an example of 2 WIMS machines. There's an Aries WIM. This is a pilot plant. Here you're looking at, bigger sample masses. And this is a Brazilian unit, which is also used for pilot plant. So in summary, if you're looking at a greenfields project, the characterization data that you generate through the assays, through the beneficiation processes, through the grade and the yield, it provides inputs for the geological model, the mining model, mine scheduling, flow sheet design, mass balance, equipment sizing and selection, plant design, and financial modeling. And if there's shortcuts taken, or if it's done on incorrect, unrepresentative samples, it compromises that whole process. So that's what we talk about now is the basis of everything that we do. And that's why it's so critical to do it correctly. If it's a brownfields plant, an existing plant with an add-on, the inputs help you confirm what flow sheet you should use, what is the mass balance, what equipment sizing and selection you should apply, what your plant layout should be, and what the economics of the expansion are. So thank you very much. Mr. Mons, I'd like to hand over to you to read the questions.
Thank you very much, Jerry. So at this stage, there's no open questions, but let me take a stab of it and start off the questions. Considering that we're here in the Northern Cape and the role cost plays in terms of beneficiation, as well as the volume profiles for the various mining houses in the area and the region, what is typically the most used processing techniques that we utilize in this area, considering the manganese and the iron ore? And should we not take into consideration the cost element as well as the volume element, would we have used other beneficiation methods?
Yeah, Pieter, do you want to answer this one?
Just quickly unlock it. So, so just to understand the question correct is, yes, there is different techniques being used in Northern Cape. I know certain mines using jigs instead of DMS. Certain manganese operations use different magnetic separations, crushing techniques to upgrade their manganese. So definitely, if we want to look at the techniques we're using for DMS for this presentation, but the density separation information that we will generate will be applicable to, for all types of beneficiation of where you're using density separation. So specifically for the jigs, for the DMS, that information will be applicable. When you go into magnetic separation, WIMS that being used in certain operations, yes, your techniques you're using for your magnetic separation can be applicable to the operations in the Northern Cape. Y'all can just make sure it addresses your question.
Yeah, I'm happy with that. And there's a follow-up question that I have, and it's a bit more based on the environmental side. If we
Jaco, sorry, can I just add on to what Pieter said before you have your follow-up question?
Not a problem.
Okay, I just want to say that you know, both Pieter and I have been extensively involved with jigging over the last 20 years, and what we've seen is that there was a stage where jigging was used because you needed to get a high density cut point to get the grade, and you couldn't achieve that with the ferrosilicon mediums that were around. But when Kumba started producing the atomized ferrosilicon, which was then taken over by Xaro, the gas atomized ferrosilicon, it was then possible to achieve those high cut densities with dense medium. And one of the things that we've seen on just about every, if you take a jig tail, it doesn't matter where it comes from, and you put it through a dense medium process, you normally get, and as a very rough rule, you can get up to 30% yield with a very good quality. So stuff misplaces to jig tails, not because of liberation, but physical misplacement. And the one aspect is the cost, but the other aspect is your overall efficiency and your recovery, and how many tons of product you're generating for each ton that you're putting in. So as Pieter says, you know, jigs are not, it's not that jigs aren't being considered, but it's that I think traditionally that what we've seen in the Northern Cape on those ores is that jigs are not as efficient as dense medium separation. And at the end of the day, when you run your financial models, what you find is that the dense medium over the life of mine is more cost effective.
Thank you very much for that one, Jerry. I see we've got two questions that came in. So the first one from Gerard is there a standard or a methodology to evaluate on how many characteristic or characterization samples is required for an ore body to be either SAIMM, REC, or JOR compliant?
Gerard, I think that's more a question for the geologists. Pieter and I, we just poor metallurgists. So, Pieter, I don't know if you've got the answer to that, but I certainly don't.
Yeah, I will just add a little bit onto that, Jeremy, is that the first step in any new ore body is to start doing the exploration work. So the geologists will come and do the block models. They will determine how big the resource are, and all the sample preparation will be done according to the SAIMM code. That code then will identify the ore body, the size of the ore body, the variability of the ore body, and then based on that ore body design, a mining schedule would be generated, and that will show you what type of ore will be scheduled into the plant at what in what variability. Let's for this discussion use it's a iron ore mine, and I'm going to mine a low grade material, and the ore is going to vary between a 55 and a 62% Fe. So when you focus on your characterization test work, you would like to focus your characterization test over that grade that you expect going to the plant. So the number of test work is not as critical, more to make sure that your test that you do represents the variability of the ore. You would like to test the ore at the 55% Fe, see what your optimum grade, optimum yield, and the same would be for ore at the 60% Fe.
Thanks for clarifying that one, Pieter. Then George has got a question that says, thank you very much for this informative presentation regarding the characterization. Your views on the use of digital optical techniques such as ROVOL as an alternative to heavy liquids, and also the effect this has on the particle shape on the dense medium separation.
Okay, so Pieter, is it right if I answer that one?
Yes, Jeremy, please.
Okay, so on the ROVOL, for those of you who are not familiar with the ROVOL, is a device that was developed by De Beers initially to track diamond breakage. And what it does is it drops a particle through a number of cameras, and the cameras take pictures of the particle from different angles, and then the software builds up a 3D model of the particle, like what they call a visual hull. And then the particle drops down, it gets weighed, and then it can go into a different density bin. So we have done comparative test work with IPP and the ROVOL on samples from a dense medium drum. And we're still in discussions with the guys at DebTech about the results. So that the two techniques do not give identical results that we've established, and we're just looking at why there are differences and what can be done about it. But the ROVOL certainly has potential. There's a claimed throughput of 1,000 particles per hour. Our experience is that could be quite a bit lower, but it is in use at Session. They've got machines there. So it's an interesting technology. I think it still needs a little bit of work before it's going to be widely accepted. In terms of the effect of particle shape on dense medium separation, it's one of those things that is just so difficult. From practical experience, I know from separations, andalusite separations there around Groot Mariku and up near Burgers Fort. Often with the andalusite ores, you get what they call flats. Those are little flat triangular particles, and they report to the underflow, the sinks of the dense medium. It doesn't matter what you do; they align themselves and they report down there. The other thing that where I've had experience is in Australia on lithium, where you've got mica present and mica booklets, and those flat plates of mica, they also concentrate in the underflow. So we know that if there's flat plates, they definitely do concentrate. When you start getting from round to slightly square to cubical and all of that, I'm not aware of any modeling or any work that's done, but the shape does definitely have an effect on separation.
Thank you very much, Jerry. So Niels has got a question that reads out as, what sampling techniques will be most representative for a large run-of-mine stockpile in order to be utilized for testing purposes? And then additional to this stockpile is blended then with different low-grade ore, manganese ores.
Yeah, I'll take that question. Yeah, so stockpile sampling is definitely a big challenge. As we know, with stockpiles, you get segregation, you get variabilities in ore. And if you go through the ISO standards, there's process you using a sample auger when you got fine material, but for large stockpiles, let's say it's a run of mine, unfortunately, you have to go back to the tried and tested method of opening the stockpile with a front-end loader, make sure you got access to the bottom part and the deeper side of the stockpiles. You need to take more sample that's been prescribed by ISO standards to clear the variability of the stockpile. You need to take samples bottom, top, and middle to address for segregation. And it's always good to keep some of the samples separate to get some sort of idea what your variability is in the stockpile. Because even if you can generate a good representative sample from the stockpile, when you're going to reclaim that stockpile going to the plant, you're going to have the same variability that is inherent to the stockpile. So yeah, that is quite critical that a lot of samples must be done, depends on the size of the stockpile and the top size of the material. Jaco, the second part of the question?
It was just the influence that it would have if you do blending of that stockpile with low and high grades here.
So definitely the variability in a stockpile is critical to understand. When you want to do blending and how you can to make sure that material gets homogeneous to your plant, what we've done at our operations is we reclaim the stockpiles and we build finger rows. Then we reclaim the stockpile, we reclaim it from the sites to minimize the variability in the stockpile, and then gives you a better constant feed into the plant for blending purposes.
Thanks for answering that one, Pieter. Then we've got a question from Anonymous that says, thank you once again for the great presentation. In light of processing of the relative core size bigger than 100 microns, how far are we, if ever close, to full dry processing, considering the threats of water availability? And it brings me to the question that I also had is, seeing the Northern Cape is water scarce, how big an impact does these processing methods have, that uses wet techniques? And considering some of the regulations, will there also be more regulations on the environmental side to these techniques?
Okay, Pieter, I'll answer that one. Dry processing has been around for a long time. Things like air jigs and various the FGX, which comes from China and so on. And they've been tried quite a lot in coal. And in coal, they've been successful as a destoning. In other words, they can remove just the heavy stuff. There's no efficiency involved. They can just sort of take out the very heavy stuff. They are, unfortunately, when you look at air as your medium, they are just not selective enough to be able to use as dense medium separation to achieve a cut at any sort of efficiency. And they've also tried adding like magnetite and that to the ore in the airbed, and really it hasn't been successful yet. And I think it's a fundamental thing. It's not because we don't have the right piece of equipment, but if you look at it, your density difference between if you use water or medium as if you let's say you're doing an iron ore and you're separating a medium density of 3. So if the iron ore particle is sitting at 4.5 and you want to separate at 3, you've got quite a bit of control over that separation process. But if you're looking at relative to air is now sitting at 0.0001. So it's 1,000 times lighter. So the density difference is that much bigger. So anything that you do is just accelerated by that big density difference. So to give you a sort of example, if you look at hydrocyclones, so when we do size classification in cyclones, we can very easily get a cut size of 100 microns or 150 microns. If you feed that same ore to a gas cyclone, you get a cut size of about 3 or 5 microns, and there's not much you can do about it. So it remains a problem. And I think the only thing that we can do there to minimize the impact of water is to look at stuff like paste thickening and all the rest to minimize the water that leaves the circuit and that can evaporate, and to keep as much of our water in recycle as possible.
Thank you. And while you on the air, Jeremy. There's a question from Thomas that's asking whether you're stating that ultra-high dense separation can successfully be cut at 4.6.
Okay, yeah, Thomas, that's a great question. If we're looking at drum separation where we're just relying on gravity, I don't know if we'd be able to achieve it with the existing grades of medium, but I think for cyclone separation, it definitely is possible because your cut density in a cyclone is higher than your medium density. And I mean, as I stated in the presentation, you know, we've run medium densities of up to 4.2 with gas atomized ferrosilicon, and that in the cyclone cuts higher, about 4.5. So definitely it can be done. I've got no doubt about that.
Thanks. And then the last one is when we're considering DMS or jig processing beneficiation methods for manganese ore, would those techniques be applicable to manganese ores for more than 45% or to the more semi-carbonaceous type manganese ores?
Sure. I haven't unfortunately seen any density distributions of a 45% manganese. I'm not quite sure what the density distribution looks like. You know, any density fractionation on that. Pieter, I don't know if you've seen.
Unfortunately not. I don't see that yet. But,
so it's difficult. It's difficult to answer that question without having some sort of, you know, a basic density characterization and understanding. Because I think in the 45% manganese, it also depends on what minerals are present. You know, if you've got your pyrolusite in that's great. But if you've got Jacobsite there, it's going to be a problem because although it's got the similar density to the pyrolusite or the Bixbyite or the other ones, it's just got such a low manganese content. So to answer, you know, to understand what's happening, you'd have to then do the mineralogy as well as the density characterization to get the answer. And once we know that, we can then make a call on the effect of jigging or dense medium separation, you know, what possible upgrade it can be achieved at what yield.
Thank you for that one, Jeremy. As all good things in life come to an end, so too that this webinar, on behalf of the Southern African Institute of Mining and Metallurgy, it's my privilege to extend a vote of thanks to our sponsors for this webinar, MEDEX, EP, and PESCO, two of our industry esteemed and experienced professional guest speakers, Mr. Pieterse and Mr. Jeremy Bosman. Thank you so much for this fruitful and enticing webinar presentation. Our session chair, Ms. Angelique Scullert, to all our national office staff members, especially Ms. Kia Shumbu and Camilla Jardine, we couldn't have done this without you, and to my fellow members at the Northern Cape Branch Committee. But most importantly, you as the audience, thank you so much for your attendance and participation, which have contributed for discussions on this topic. I'm sure that if you have any questions, you can get into contact with us and we can try and get Pieter and Jeremy's view on that. Remember these characteristics next time for that you're going to use for a resource optimization study, especially on the iron ore and manganese side. Ladies and gentlemen, until next time, keep your fingers on the pulse with SAIMM and stay safe. We thank you.
Thank you.